I enable microphone for you. Anybody understand what I say? Do you understand? Okay, تشکر محمد الخفاجی. Mr. Abdulrahman Jaburi, Hassan Zayer, Murtaza al-Mashhadi, understand? تشکر al-Hasnawi, Hassan al-Hasnawi, تشکر. We teach metric space before, almost 4 or 5 weeks ago. We teach metric spaces. This is a remark of metric space. This is a remark of metric space. Okay. You know that what is the open interval? In the R, in R2, in R3. Okay. In R, the interval, open interval is, as you see here. In R2, the circle is interval. Okay. In R3, the sphere is open interval. Okay. Open sets. Okay. Then this is open sets. I write here. Open set. In here is interval AB. In here S1. In here is S2. Okay. Okay. You see that R, R2, R3, and Rn are topological space. Okay. The spaces are R2, R3, and H are topological space. Okay. In R, A و B, that A و B belong to R. Okay. The open sets in R2 are circle S1. Indeed, I write x and radical 1 minus x power 2, that x belong to R. Some of you write x to power y2, such that x, y belong to R. This is true and the above is true. Okay. The open sets in R3 RS2. I write x, y, z such that x2 plus y2 plus z2 is 1. Okay? A sphere, Korra in Persian. A sphere, circles, interval, open interval. Open interval. Okay. As you see, R, R2, R3 are metric spaces. Okay? As you see, R has metric spaces, R2 is metric spaces, and 8 are metric spaces. Metric spaces. Okay? Every metric spaces are topological spaces. Okay? Every metric spaces are topological spaces. Indeed, we have this diagram. This is topological spaces. This is metrical spaces. Okay, every metrical space is topological space. But we have some topological spaces that are not belong to metric spaces. Okay, we have some metrical spaces here that are not topological spaces. For example, let X be a non-empty set and define two P and X. Okay, P and X is not a metric space. It's not metric spaces. But it is a topological space. Indeed, X and tau is a topology that is not metrical space. Okay, this is very simple. Okay, let X and D be a metrical space. Okay, put tau induced by metric. The topology induced by metric is defined as U subset of X, that U is open in XD. Okay, this is a topological space. This is a topological space. This is a topological spaces. Okay. Thus, okay, excuse me. Tau D is a topology on X. We call Tau D the topology induced by D. Then every metrical space X and D is a topological space. Okay, this is a proof for the fact that every metrical space is a topological space. Okay, everyone understand? Abdurrahman al-Jaburi, Abdul Salam Taha, Hassan al-Hasnawi, Zahir Hanum, Hassan Zahir Hanum. Understand? I enable the microphone for you and you can speak with me. If you don't like to speak, you can type. Type in the right hand of you. In below, you can type. You can type me that you understand what I say or no. If you don't understand, please tell me. I repeat it again for you. If yes, I continue my teaching. Okay. Uh, I give you an interesting note. Uh, Different topology on X. Okay. For example, let X be R, real number. Then we have a topology توهي empty set and X. This is the trivial topology. Is trivial topology. Trivial topology. Topology on R. Okay. Another topology T2 is the power set of topology. Okay. Power set. This is discrete topology. Topology on R. Another topology. Topology induced by metric space. Okay. Induced by metric space. Metric D. Okay. Metric D. Okay. You see that there are many topologies on a set. There are many topology on a set. Okay. There are many topologies on a set. Okay. Now a question arises. Now we have a question. Let X2 be a topological space. Okay. Is there any metric T on X such that this topology is equal to topology induced by metric space? This is a good question for us and have a good answer. We have a good answer for it. Okay. Okay. I repeat it. Let X and 2 be a topological space. Okay. Let X be a topological space. Is there any metric D on X such that 2 is equal to 2AD? 2AD, this is topology induced by D. Okay, this is the natural topology on X. Is there any metric? What is your answer? metric C top Kasana Lasnavi. This is a question that the answer is yes or no. Yes or no. What is your answer? Okay, Kasana Lasnavi write no. Al Khafaji says no. Okay, what is your answer, Sajjad? What is your answer, Abdul Rahman? Okay. Which metric space? Example, metrizable topology. Okay. Now I give Hausdorff spaces. Hausdorff. Um, before I give a Hausdorff space, I define the metrizable spaces. Metrizable is topological space. Okay. Let X to be a topological space. Then X2 is called metrizable if there exists or there is a metric D on X such that tau D is equal to tau. Okay. Then we say that X2 is a metrizable. X2 is a metrizable. We have some topological space that is metrizable. We have some topological space that are not metrizable. Some topological space are metrizable and some topological space are not metrizable. Okay, I give some example here. Example 1. Okay, X with power set topology on it. Okay, is metrizable. Okay, I define Txy by x equal to y1, excuse me, 0, x is not equal 1. Okay, this is the discrete metric. Okay, this is discrete metric. D is the discrete metric, we have power set is equal to topology induced by this is topology that here. Okay, this is equal to topological space induced by T. Indeed, we say that discrete topology is metrizable. Okay, discrete topology is metrizable. Okay. Example 2. X with trivial topology. What is trivial topology? Trivial topology is phi and x is not metrizable. Is not metrizable. Okay. Indeed, there is not any metric on x such that OD is equal to 2. There is not. There is not. Okay. Then we must have some condition on a topological space that let us to consider it as metrizable or not metrizable. Okay, we are going to find the condition on topological space x2 such that became it metrizable topological space. Okay, I find some condition on topological space that let us find a D that D is equal to 2. Okay. The first condition is Hausdorff. Okay. What is Hausdorff space? Okay. I finish my teaching here. And come back to you after 10 minutes. After 10. And I'm going to teach Hausdorff spaces. Hausdorff. Okay. Hausdorff is a German mathematician that defined the Hausdorff space. What is it? Let x2 be a topological space. If for every point x, y belong to 2, there are u and v belong to 2, such that x belong to u, y belong to v, u intersection with v is empty, then we say that x2 is a Hausdorff topological space. Okay? If for every 2 points there exist 2 open sets, they are open sets, such that x belong to u, y belong to v, u intersection with v is empty. In diagram, we have such space x, y. Okay, this is u, this is v, u, v. Okay, you see that x belong to u, x belong to u, y belong to v, u intersection with v is empty. Okay, for every 2 points, for example, this is z, this is w, this is p. Okay, we must find open sets here, that they are in it and they are disjoint. Okay, every metric space is Hausdorff. For example, let us consider R. Okay, we choose 0 and we choose 1. Okay, the distance between 0 and 1 is 1. Okay, this is 1. Okay, in center 0 and I take R 1/3. Okay, 1/3. This is the open sets here, and this is the open sets here. Okay, this is V, this is U. You see that U intersection with V is empty. 0 belong to U, 1 belong to V. Okay, and for every point we have such open sets. For example, here and here are 2 disjoint. Okay, point. I give this interval and this interval. Okay, this is U, this is V. They are disjoint. They have not any intersection. Okay, then R with T is Hausdorff. Understand? Again, okay. I explain it again. This is R. Okay, metric space, Euclidean metric on it. Okay, I choose 2 points. For example, this is T, this is Q. Okay, uh, we know that D, P, and Q is R. This is R. Okay. I divide it to three space, three segments. Okay. Three segments. Okay. Then this is an open interval U. Okay. And this is an open interval V. Okay. You see that P belongs to U, Q belongs to V. Okay. U intersection with V is empty. Kaslan al-Hasnawi, understand? Okay. This is the first example. The second example, R2. Example 2. R2 with Euclidean method on it. Okay. Okay. I have, for example, this P and this is Q. Okay. We know that there is a distance between A. For example, R. This is R. D, P, and Q is R. Greater than 0. Okay. This is R. Okay. Again, I distinct it to three phase. 1, 2, 3. Okay. Then here I give a circle around Q and I give a circle around here. Okay. This is S1 around P and this is S1 from Q. I write it Q, U, this is V. You see that P belongs to V, Q belongs to U and V has not any intersection. Okay? Has not any intersection. Understand? Anybody understand? Okay. I give another example. Example 3. In three-dimensional space R3, with Euclidean metric. I have 2 points here P and here Q. Okay. Again, I give a line between P and Q. Excuse me. For example, this is R. D, P, and Q is R. Greater than 0. I divide it to 3 pairs. Okay. Then I can give you a sphere here and a sphere here. I say it U, I say it V. Okay. U intersection with V is empty. P belongs to U, Q belongs to V. Okay. Then R3 with Euclidean metric on it is Haskell. Okay, I give you a theorem here. By this example, I can say that theorem. Every metric space is Haskell. Okay, every metric space is Haskell. Okay, I prove it for you. I prove it for you. Proof. Let Xt be a metric space. For every distinct points x, y belong to x, let us put u defined by n x r and v defined by n y r are our three where dx y is r. Then x belong to u, y belong to v, and u intersection with v is m. Okay, this is metric space. Okay, this is x, this is y. Okay, I see that their distance is r. Okay, then I choose trig space. I give a open set around x and around y. Okay, this is n, x are our tree. This is N, Y are our tree. And what is N? Neighborhood. This is N, neighborhood. Neighborhood. Atjar, atjar. You say in Arabia atjar. Atjar summatar. Atjar. Hamsayegi. We say in Persian Hamsayegi. You say atjar. In English, it is neighborhood. It is neighborhood. For example, in R, okay, this is 0. This is a neighborhood. Okay, if this is -1, this is 1, and we say N0, and if, for example, this is R2, this is 0, for example. Okay, 1. This is 1. This is N 0, 0, and 1. Okay. This is center. This is radius. And this means neighborhood. Okay. Everybody on Al-Jawar. Yes. تشكر قسطان الحسناوي. شكرا جزيلا. Everybody understand? Everybody understand what I say? الخفاجي تشكر. الحسناوي تشكر. شكرا جزيلا. Theorem. Every metric space is Haskell. Proof. Let X and D be a metric space. Okay. Let X be a metric space. For every distinct form, X and Y belong to D. I put X, U as a neighborhood of X with radius R over 3, and V neighborhood Y with R over 3. Okay. Then X belong to here and Y belong to here. And U intersection with V is in. Then every metric space is possible. Okay. Some exercise. I give you some exercise. Before exercises, I give a corollary. We have theorem. Metric space is Haskell. Okay. Can you give me a corollary? Natija. Can you tell me a natija from this theorem? Yes. Tell X. Okay. Can you tell me Hassan al-Hasnavi? In logic, mantel. P then Q is equal to opposite Q is opposite P. Okay? This is a hint for you. Okay. Can you tell me a corollary? Everybody, can you tell me a corollary? Okay. I give you a corollary here. Give me a okay. I can say that if it is not Hastor, then it is not vectorizable. Okay, this is opposite Q, then opposite P. Okay, I write it as follows. Corollary. Corollary. Every topological space that is not Hastor, then it is not visible. Okay. Understand, everybody? Understand? تشكر قسطان الحسنابي. The other people, Muhammad al-Khafaji, understand? Jazila. Okay. some exercises. Exercise 1. Introduce a topological space that is Hastor but it is not metrizable. This is the first exercises. Exercise 2. Exercise 2. Let X, not entity set, be a finite set and to be a topology on X. Let X2 be Hastor. Prove that to is X. The discrete topology. Indeed, this is discrete topology. Discrete topology. Okay. Another exercise. Exercise 3. Let Xt be a metric space. And Y be a subset of X. Non-empty. Then D induces a metric on Y. Show that D Y is a metric space. Okay. I hint exercises 3 is very trivial. This is X with metric space. Okay. This is Y. Okay. I solve it for you. You define a D on Y. I show it with DY. Induced by D. What is DY? DY X Y for every X Y belong to Y. Defined by as follows. This is dxy if x, y belong to y, and 0 if x, y is not in Y. Indeed, if it is X and Y, then they are dxy. But if is here, then it is 0. Okay? Dy is called induced metric on Y. Induced metric on. Okay. I hope. I hope this exercise. Okay. A question. We have a question here. Question. Let a topological space X2 is metrizable. Okay, is the metric is the induced metric is the metric D on X with 2D is equal to unique is unique is unique is unique. Okay. Understand what I say, everybody? Okay. For example, there is a metric T on X such that 2AD is equal to 2. Is the unique T? Okay. This is a good question. This is a good question. I say that no. I say that no. I give an example for you here. This is the final case I teach in this time. Let to be the power set of X discrete topology. Okay? Is discrete topology on X. For every n belonging to natural number, define dn from X times X to R positive such that dn xy is equal to n. Okay, is equal to n if x not y, if x y2 is 0. Okay, day 1 xy is 1 0. Okay, J2 2 0 and it. Okay, the topology induced by D1 is X. The topology induced by D2 is X. And Dn. The topology induced by Dn is X. Okay. But you see that D1 is not equal to D2, and they are not equal because n is not equal in them. Okay. Then the metric is not unique. The metric is not unique. Okay, I finish my teaching here. If you have any question, I am in your service. If not, you can leave the class. Okay, تشكر شكرا جزيلا. Goodbye everyone. Goodbye.